Sapienza di Roma. We'll speak about spherical surfaces with conical points.
Thank you. Thank you for the opportunity of speaking here. So I will report about the states of our knowledge about surfaces with constant curvature 1 and conical singularities. And I will also describe some of the results we had with Eremenko-Panov from King's College of London, and joined with Alexander Eremenko and Eremenko-Panov in another paper. So first I will, okay, so this,
sorry,
yeah.
I feel this side, and if you want to be in
Closer,
frame,
yeah.
you can go
Okay,
near the
yeah.
side.
Let me, okay. Here?
Yeah, yeah.
Okay. Okay, so first of all, I will speak of some motivation. So so why we're interested in spherical surfaces, and then also of course some basic things. So for example, what are spherical surfaces with 2 or 3 conical singularities in genus 0? Of course, what is the Gauss-Bonnet constraint, and what is the monodromy attached to such a metric, to such a surface, and what is its developing map. And then I will list a few results, which are known. Actually, there are many results, but they overlap in a strange way, so it's a bit rhapsodic, depending on the fact that different communities have worked on these problems, both from analysis, complex analysis, real analysis, and geometry. And okay, first I will tell you what is known about the unpunctured case, which is the classical case, uniformization theorem, and then we will see some phenomena that somehow distinguish between what will be called the subcritical and supercritical cases, or sometimes we'll distinguish between the case with when all angles, the singularities, are smaller than 2 pi, or when there are some angles which are bigger than 2 pi. Or sometimes there are results which distinguish the genus 0 case from the other cases, so positive genus. So this to say that you will see that the results are a bit not exhaustive, but they overlap in a strange way, non-organic way for the moment. And then I will pass and describe our last work on genus 1 surfaces with 1 conical point. This is almost one of the simplest cases. Probably the simplest cases is genus 0 with 3 conical points, but then this is the next one. And in this case, we will describe the topology of such modular space. Okay, then I will describe how we reduce this problem to a problem of spherical triangles, basically. Okay, and even the topological description, you will see that there is a special case when the angle is an odd multiple of 2 pi. Yeah, so we will see if I can cover all of these or just parts. And so let's start with some kind of motivation. Sometimes if you have a surface with some metric, surface for me is always a 2-dimensional real manifold with some metric, then you can attach to it, and it's oriented, you can attach to it the underlying complex structure, conformal structure. So it gives a map from the space of metrics, whatever topology you want to put on it, to space of complex structures. So for quite a long time, the people wonder about if given a complex structure, there is a canonical metric with the given underlying conformal structure. This is a basic problem, and really it underlines much of the study of the space of complex structures on surfaces. And the reason is that out of a complex structure, it's very difficult to pull out some quantities. You can, of course, you can pull basically, the only quantity you can pull out of it is extremal length, or combinations of extremal length, which is really a conformal invariant.
Extremal what?
Extremal length. Length in one-dimensional complex analysis. But of course, if you have a preferred metric, in a canonical metric in each class, then you can attach to this conformal class all the quantities you can extract from such canonical metric. And then usually from canonical metrics you can extract a lot of quantities, lengths, angles, ratios, combinations, and so on. So this is I mean, the problem of attaching a canonical metric I mean, is almost everywhere in three-dimensional manifolds. People started from topological objects and tried to geometrize them, or now in higher dimensional complex manifolds, people are trying to look for some kind of canonical metrics like Keller-Einstein metrics. So it is a problem that is very ubiquitous in geometry. Okay, so sorry. So this is what I was saying. So out of a preferred metric, you can usually compute, you can extract information about symplectic structures. You can construct symplectic structure on the moduli spaces. You can construct Riemannian structures on the moduli space of metrics and so on. Also, if you have a metric, you can define also holonomy of the metric. So you take a loop and you see basically parallelly transporting the tangent vector, you see what happens to tangent vectors. And if the metric, when we are working with constant curvature metrics, there is a slightly different notion of holonomy. I mean, in the flat case is the same. In the flat case, this is exactly the holonomy. And if you imagine the flat case like a cone and so on, the fact that it's flat, tells us that the holonomy only depends on the homotopy class of the closed loop, but it does not depend on the actual loop. Similarly, so this fact also is reflected on the fact that locally the surface looks like a piece of plane, Euclidean plane, and the gluing maps, change of charts, are isometries of the Euclidean plane. So quite similarly, in curvature 1 or in curvature -1, in curvature 1, all surfaces locally are made of pieces of the sphere, and the change of charts are isometries of the sphere. So this, similarly to the Euclidean case, gives us a representation of the fundamental group of the surface to the group of isometries of the sphere, which in this case is SO3. So it keeps just track of all the change of charts needed you patch your loop with this change of charts, and then you compute what happens when you are back to the initial point. And similarly, in the hyperbolic case, you have the group G is the group of isometries of the hyperbolic plane, so it's a PSL2R. So one classical problem, especially in the case of the hyperbolic case, is to detect which representations of the fundamental group are actually monodromy representations. This is solved if S is a compact surface, but it is still open if S is a surface with punctures and possibly conical points. Okay, so what is known in the unpunctured case, so with no singularities? If there are no singularities and the genus is at least 2, it is known that there exists a unique metric, hyperbolic means constant curvature -1, in each conformal class. This is the classical uniformization theorem by Gabriele and Poincaré. And it holds also, it's even, in the flat case is even more ancient, so tori have naturally a flat metric, which is unique up to rescaling. So you obtain it from the complex plane, just quotienting out a lattice. In the case of the sphere, genus 0, actually, if you fix the sphere, certainly you do have a round standard metric on S2, but actually there is a three-dimensional family of metrics, which are the same, conformal to each other, because you connect on S2 by PSL2C, so you identify S2 with CP1, and you connect on it by projective transformations of CP1, and those who are in SO3 preserve the metric, but those who are not in SO3 do not preserve the metric. So actually the family of metrics is parameterized by PSL2C mod SO3, which is exactly three-dimensional family. So they're all conformal, but they're not equal. In any case, there is certainly there is a metric, but it's I mean it's sort of trivial case. For example, in the case of the uniformization theorem, how Koebe solved it? So you fix a background metric on S, any metric in the conformal class you chose, and then you are looking for another metric in the same conformal class. So the new metric H should be proportional to H0. So it's a positive function times H0. And this positive function, I call it e to the 2u, where u is a real function. So the condition that this new metric has curvature -1 can be rephrased in terms. I'm thinking, for example, well, I was speaking of the first case, but in all cases, if you want constant curvature k, or even non-constant, but say suppose constant curvature, then it can be rephrased in terms of this scalar differential equation, semilinear differential equation. There is this term that makes it nonlinear, this e to the 2u. So this is sometimes the term that one needs to study to keep control of this term. So this is the equation that Koebe solved. And this is also the equation that one wants to study even in the presence of singularities when you want to find another metric in the same conformal class of the given one. So that's why analysts got interested in this problem, because they were interested in solving this differential equation. Okay, now let's pass to the case where there are some points where we will have singularities. So let's call these points x1, xn. And we study constant curvature metrics with some prescribed behavior. So I will call a spherical metric would just mean that the curvature of the metric is 1 away from these x1, xn points. And then there will be conical singularities at these points, and I will say shortly what it means. Basically, they look like a cone. And the spherical surface is the triple, right? So the surface, the bark points, and the metric. Okay, so away from the points, so S dot is the complement of the singularity. So away from the points, this is really locally like a piece of S2. So it's a piece of the sphere. And globally, you can always cut this surface into triangles, like convex triangles, so portions of triangles in S2 with angles smaller than pi. So you can obtain it as a gluing, like you can imagine you can triangulate your surface basically. And each triangle is a convex triangle. And of course, when you glue them at the vertices, you might or might not have a singularity. And those will be conical points. The same you can do, I mean, the same concept hold if you replace in the flat case the sphere by R2, or on the hyperbolic case the disk, the hyperbolic disk. So what's the, yep?
Gabriele, is it true that any spherical metric can be obtained by means of pulling back the metric on the sphere by some meromorphic function?
No, not in general. Because if you do that, you have two things. You have that the angles must be multiple of 2 pi. And the second thing is that the monodrome A must be trivial. So this is actually equivalent. These two conditions must hold. Otherwise, you have to go to the universal cover, and you can pull it back at the level of universal cover. Okay, so what's the aspect of let me also put a picture, of a conical point. So if you want to look at pictures, say if you take a small angle, smaller than pi, you can draw two meridians in the sphere. You consider the sector between these two meridians, and you glue the two meridians one to the other, and you attain a football. And a neighborhood, so this is a conical point, and a neighborhood of any conical point with the same angle looks exactly like this. So this is the aspect. In coordinates, basically this is the aspect of the standard metric of curvature k. So if you put k equal to 0, it's Euclidean. If you put k equal to -1, it's hyperbolic. If you put k equal to 1, it's spherical. And so this is the smooth metric of curvature k. If you take the pullback through the map z goes to z to theta I, where theta is some positive real number. Then you plug in, you substitute, and then you get the local analytic expression. Here, theta I is any positive number, so this map need not be univalued. This can be multivalued, so this theta I can be square root of 2. And then you will get the aspect of a metric with the angle square root of 2 times 2 pi. So the actual angle in the standard terminology is theta I times 2 pi. Okay. So let's look at some examples, the simplest ones. Okay, so in the case of genus 0, with no conical points, of course we have the round sphere. There is no, I mean, it's not possible to have just one conical point. I mean, if you have one conical point, then that conical point must be smooth, actually. The case of two conical points already shows some interest. So here there are two examples, the only two examples. You can have a football here, or you can have a cyclic cover of the sphere branched at 2 points. In the first case, the 2 points, the two conical points are at distance pi, necessarily. And the two angles can be arbitrary, but equal. So this can be, I don't know, 25 pi and 25 pi. And then how do you attain this? I mean, if the angle is small, we have already seen it, cutting just the sector between two meridians. If you want a large angle, then you cut 2 million of these strips, and then you glue to each other, and then you can obtain an angle which is as large as you want. Here, there's a different situation. This is a cyclic cover of order 2. So you start with the round sphere, you pick 2 points at any distance, so the distance between 2 points on the sphere is at most pi, and then you take the cyclic cover branched at these 2 points. This is a double cover. So in this case, the angles are arbitrarily but integers, positive integers, and the distance is arbitrary but at most pi. So these are all, the only Trojanov classified them, it's easy. These are the only two possibilities. Okay, let's go on. Let's look at spherical triangles. So this is how I usually imagine a spherical triangle. So you just pick. Yeah.
Please return.
Yeah, sure.
And this is a two-fold coloring of the sphere.
Yeah.
And it can be a three-fold coloring.
Yeah, sure. You can start with the sphere. You pick any 2 points. Then, okay, you want to take the triple or fourfold cover of the sphere. So topologically, you can cut here, and then you take 3 copies of this. Okay, and then if you call A1 B1, A2 B2, A3 B3 the shores of the cut, then you can glue B1 with A2, for example, B2 with A3, and B3 with A1, and so on. You can do it with as many as you wish. This is, yeah. Okay, so as for spherical triangles, the first one you imagine is this one. This is a convex spherical triangle, so it's embedded in the sphere and the internal angles are smaller than pi. But you can see immediately that you can have another possibility, which is that you embed this in a half sphere, you take the complement, and then you get this one. This is not convex because here it has angle bigger than pi, but it's still embedded. Or, for example, you can take the complement in the sphere of this T. There is also a triangle. So, for me, a triangle is just a disk with boundary. So, topologically, is a disk. In the internal part, it has curvature 1. The boundary is piecewise geodesic. So, and the fact is that these are 2 examples of embedded, but by definition, there is no reason why such triangles shall be embedded in the sphere. And of course, if you can construct a triangle which is an angle which is bigger than 2 pi, certainly cannot be embedded, because if it's embedded, it's necessarily smaller than 2 pi. Okay, so if you pick a triple of angles, then you almost always, now I will tell you what it means, there exists at most one triangle with angles pi theta 1, pi theta 2, pi theta 3. So these triangles characterize the triangle if such triangle exists. And of course, they also give you the area by Gauss-Bonnet. So sometimes triangles with these angles do not exist. These are the type of exceptions to uniqueness. The exception is something like this. This is basically a football. Sorry, half a football. So you cut just the sphere, two meridians in the sphere. These are north and south pole. And then you mark a third point on the meridian, and you pretend this to be another vertex of angle pi. You see here that if you keep theta 2, theta 3, and this theta 1, which is pi fixed, the triangle is by no means unique because you can still move this point A1 along this edge. So in this case, these are very few cases that can be characterized, then the triangle is not unique, but you can slide this conical point. But in all other cases, these are essentially unique. So the question is, for which triple of angles does a spherical triangle exist? And one can think that the only constraint is to have positive area, so the only constraint is the one we've seen, but actually this is not true. So it was known that in the convex case, a triangle exists if and only if the supposed area, so these numbers must be positive, of course, but also it must be smaller than twice theta 1, twice theta 2, or twice theta 3. The reason, one reason one can check is the following. If you have your triangle, let me draw it this way. This is your triangle. You can embed your triangle inside, this is a diagram, so it's the region that we constructed, enclosed between two meridians. Yeah. So the area of such triangle must be smaller than the area of the diagon. And the area of this diagon is exactly 2 theta 1. Theta 1. So this is exactly why this area should be smaller than 2 theta 1. And this is enough in the convex case. But in general, if the triangle is not convex, so the angles are not convex, then this is not enough. And actually here, I'm drawing the regions in the space of angles for which triangles exist. So let me describe this picture. So this is a three-dimensional space. This is the theta 1 axis. This is the theta 2 axis. And this vertical is theta 3 axis. These are the integral points, these ones with the dots. And this green simplex with these 4 green vertices is the region inside which all triples which are inside correspond to convex triangles. So if you pick a point inside in the interior of this, then there exists a convex triangle. If you want to know what's the region in this other cube for which convex triangles exist, then you have this other blue simplex, which is obtained from the green one by reflection. So it's not true that any time you pick a point, you do have. So you pick a point here, you don't have a triangle corresponding to these angles. So this result, so the general answer was proven by Eremenko in 2004. So basically all the angles which are admissible are obtained from this green one, just reflecting along every time you have, so inside this cube there is this green one, then you reflect along this face of the cube and you get this blue one, and then you reflect along this other face and you get another simplex here, and so on. So it's a collection of inequalities that geometrically means you obtain all the domain by reflecting this green simplex. Okay, so in general, there is a simple constraint that necessarily must hold. We have seen it already in the case of triangles. So if you are in the situation we have already seen with the metric H on S with conical points x1, xn of angles 2 pi theta 1, 2 pi theta 2, 2 pi theta n, then if you look at the Gauss-Bonnet formula, in the Gauss-Bonnet formula you have, without boundary, you have an integral of the curvature of the metric that must give you the Euler characteristic. Here, the metric has constant curvature 1, but at the conical point, if you smoothen them a little bit, it's like having a very concentrated curvature. So it's like having a delta of curvature concentrated there. So this must be taken into account in the Gauss-Bonnet formula. So the angle 2 pi theta I at xi gives a curvature which is a delta at xi of mass 2 pi 1 minus theta I. So you see from this that if theta I is 1, the angle is 2 pi and there is no concentration, of course, because it's smooth. If the angle is smaller than 2 pi, then the curvature is positive because the aspect is this one. And you see that this, if you smoothen a little bit, looks like something of positive curvature. If the angle is bigger than 2 pi, then the curvature is negative. Now, it's very difficult to draw a picture, but if you try and draw something, then, okay, that's...
So we can think about this delta as a point of mass of this path.
Yeah, the curvature has that mass there, yeah. So when you write down the formula, you have, this is the contribution of the area, I mean, of the smooth part, the integral of the curvature on the smooth part. This is the integral of the curvature on the singularities, and this must give 2 pi times the Euler characteristic. Now, if you take this part of the singularity on the right and you incorporate in this, so basically instead of Ks, you take Ks plus this part. So you have this formula. So the curvature times the area must be equal to 2 pi times this weighted Euler characteristic, weighted with the angles. And basically, you see that here, because the area is always positive, the sign, if the curvature is constant, the sign of the curvature must be the same as the sign of this weighted Euler characteristic. So basically, if we want to deal with spherical surfaces, then this weighted Euler characteristic must be positive, which we will assume now on. Okay, what are the type of problems that people wonder about these surfaces? Okay. First, you can construct a moduli space, so a space that parameterizes all surfaces of genus G, assigned genus G, with n conical points, and with these conical points of assigned angles. So you assign the genus, the number of points, and the angles, and you want to parameterize all possible surfaces. So then...
And the total sum of the angles is fixed.
No, each angle is fixed. Here I'm fixing each angle.
If you know the genus G, then the total sum of the angles must be...
No, it must be, there is an inequality. You see, from this formula, it follows if you pick k equal 1, the area is positive, yeah, the area varies, and so this must be positive. So the only inequality is that this quantity is positive. Yeah. If you have equality only if you want something flat. Okay, so you can construct such a space, and the first question is how this looks like topologically. Then one can ask for finer questions, but the first thing is whether it's non-empty, whether it's connected, whether it has infinitely many elements, and so on. The second interesting question is the following. We discussed at the beginning the fact that if we have some metric on a surface, then we can assign the underlying conformal structure. This gives a map from this space of metrics to this, which is the space of all possible complex structures on surfaces. This is the moduli space of Riemann surfaces. So if you study this map, basically if you study studying the fibers of this map is the same as fixing a conformal structure and studying what are the possible metrics in the assigned conformal structure. So this is very similar to the uniformization problem that was discussed at the beginning. The uniformization problem was saying that in each conformal class there is, in the hyperbolic case, there is one metric. So it was saying that this map is bijective in the hyperbolic case. So this problem, studying this map is like uniformization. Studying this is analogous to studying all the space of all metrics. Okay, so the existence of a spherical metric in a conformal class is the same as saying that this map is surjective. So for every conformal class there is a metric. The uniqueness in each conformal class is injectivity of this map. So many statements about existence, uniqueness, or similar statements can be phrased in terms of topological properties of this map. Okay, just a brief digression of what is known in the non-positive case, because this is much easier. So in the non-positive curvature, so hyperbolic or flat, you can construct still this moduli space, and you can construct this map. And it was shown in full generality by Troyanov that this map is a homeomorphism. So basically, in each conformal class, there exists exactly one metric. So this is a bit more than Koebe's theorem, because in Koebe's theorem we were dealing with smooth metrics. Here we are assigning singularities. So in Troyanov's case, even if you assign singularities, then there is a unique metric in each conformal class. And the same also in the flat case, if you normalize so that the area is 1. So what are the ingredients in this proof? There are two ingredients. The first, you have to show that the metric exists. To show that it exists, it formulates the problem in a variational way. So there is a functional, and then you show that this functional is coercive, and so there must be a minimum point, and then it shows existence. The fact that the curvature is non-positive in the differential equation that yes allows us to use a maximum principle and have uniqueness. We will see that this second, I singled out these ingredients because this second thing will fall in the positive curvature case. So in the spherical case, this tool of maximal principle will never hold. Sometimes the first one will hold and one will have existence, but we'll never have this tool. Okay, so what is known about MSGN is the moduli space of spherical metrics, genus G, with angles θ1, θn. So the first result is there are certain metrics we have seen in the case of triangles which are a bit special. Remember the case of triangles, there were certain triangles that were not characterized by their angles. It was a triangle of this type. For example, the analogous, if you glue these two, is a football. So this is a football. So the x3, and here there is a point x2 of angle 2 pi. American football, yeah, or rugby ball. So what is special about this? This is special the fact that it has extra symmetries, extra conformal symmetries. So you can, like in the sphere, if you have the sphere with north pole, south pole, and the point here, then you have self maps which are conformal and that somehow suck everything in the direction of the north pole. Basically, if this is the Riemann sphere, this is infinity, and this is 0. So you have the map that sends z into lambda z. This is a map that, if lambda is smaller than 1, sucks everything towards 0. So the same we have here. So in this case, you remember this case was obtained from the sphere just taking two parallels and identifying them. And then you can apply the same map with the real lambda, and then you get kind of flow that pushes everything in that direction. So these type of metrics, which have this kind of extra symmetry, are called coaxial. Sometimes they do occur. They're rather special. But they do occur only, not for any set of angles. Actually, if you are in this, the set of angles is a subset of Rn, then if they occur, then you are on certain walls. So there are certain hyperplanes on which this phenomenon can occur. Away from such hyperplanes, it doesn't occur. And these hyperplanes cut this Rn into chambers. And somehow one expects that in crossing the wall from a chamber to another, something topological should happen to the moduli space. So the first most basic property of a moduli space is whether it is empty or not. In general, in full generality, we showed with Panov that if the genus is at least 1, then and Gauss-Bonnet holds, then this moduli space is non-empty. So, I mean,
so the Gauss-Bonnet is the only restriction.
Yeah, for genus at least 1 is the only restriction to the existence of some points. So basically, we constructed by hand this one point here. The surprising thing is that in genus 0, the Gauss-Bonnet rule is not the only constraint. Of course, it's necessary, but there are further constraints. So not all angles are allowed. One phenomenon you have already seen in the case of triangles. In the case of triangles, the Gauss-Bonnet, the fact that the sum of the angles were bigger than pi, was not enough to ensure existence. There were other constraints. Other properties of such moduli space, which this is just non-emptiness, this is something about local properties. So this moduli space is a real analytic, almost a manifold. I mean, there are some singularities, but it is essentially a manifold away from this strange matrix, which I call the coaxial. So almost everything is a smooth manifold, dimension 6G minus 6 plus 2n. So it has the same dimension as the moduli space of Riemann surfaces. It is real analytic. And one also knows the local model. The local model, is the space of representations. So you take a certain space of representations of the fundamental group of the surface minus the conical points in SO3. And then basically this space of representations, which is easy to construct, models the local aspect of this. So this type of singularities that one has is a type of singularities of a real algebraic variety.
First of all, what is the dimension of this moduli space?
Of which one? The representations?
Starting with
This.
MSGN.
This one?
Yeah.
Yeah. 6G.
Of dimension 6G minus
Yeah.
6 plus 2.
Yeah. There are some exceptions. So at coaxial metrics, so at these singularities, the dimension can jump. So there are some moduli spaces in which all metrics are coaxial, and then the dimension is bigger. We will see one example. But ordinarily, this is the dimension. So also, which we haven't exploited yet enough, but if no angle is integral multiple of 2 pi, then this moduli space, which is also a manifold, an orbifold, has a symplectic structure. The symplectic structure is actually pulled back from the space of representations. Space of representations always has a symplectic structure.
And the only singularities are orbifold ones.
If you are away from coaxial metrics, yes. Away from those exceptions, those metrics is just orbifold. Yeah.
This is an orbifold.
Yeah.
And what kind of singularities you obtain at coaxial metrics?
At coaxial metrics, I think that there should be results by Goldman and Milson that it should be quadratic singularities. Yeah. So other topological properties, if we are, now you see that this gets a bit more rhapsodic, so it depends on the genus and so on. So in genus 0, if all angles are integral, this is connected. This is similar to some kind of Hurwitz space. Why I'm saying similar? Because here, when it's genus 0 and the angles are integral, as you were saying at the beginning, all metrics are obtained through a map to P1 by pulling back the round metric. Here, though, we are not asking what happens over a branch point. We are not prescribing the pattern over a branch point. We are just prescribing the ramification orders in the source. So it's not the same, exactly the same space. So this is the result by Liu and Osserman that this is connected. With some other non-integral theta, with Panov, we showed that in general this can be wildly disconnected. So it can have a number of components that is of the order 3 to the n. So it can grow exponentially with n. So especially when some angles are small. So this is in general not connected. This is also in progress. In general, this should be general. There are though finitely many connected components, but all of them are non-compact of finite type. Finite type means it's just a finite union of contractible. So if there's a cellular decomposition, and with finitely many cells. Of course, except in the case of genus 0 with 3 points, because in this case it's just a union of points. So.
For sure, you have addressed the question of how to compactify this.
Well, we are thinking about it, but it's by no means obvious because it promises to be more complicated than the flat, than the translation case. I mean, in the order of complications, you have the translation case, which was done by Bainbridge, Chen, Gruszewski, Gendron, Gruszewski, Müller. But then you have the flat case, flat non-translation, and then you have the spherical, which is probably a bit more similar, but a bit more complicated. So we don't know if there are easier compactifications, though singular.
They have done for the flat case for arbitrary angles.
No, we haven't. I imagine that there's something similar to their compactification can be done, but we haven't. So what is known about the forgetful map, the one that attaches the underlying conformal structure? So from just as theoretic properties, this is surjective, so there is existence of a metric in each conformal class in the subcritical case. Subcritical case is a strange thing apparently. It's just a numerical condition, so this characteristic, weighted Euler characteristic, should be less than the minimum of this twice theta I or 2. So this was proven by Troyanov in 1991 using the same techniques, variational techniques. Here, as I was saying, there is no injectivity because there is no maximum principle, but the same technique shows surjectivity. So what is this condition? Why is it there? Basically, this is a condition of non-degeneracy. So sometimes when you minimize the functional, when you try to minimize the functional, these metrics create some bubbles. So they're trying to make bubbling. What does it mean, bubbling? That you're trying to look for a metric, and then while minimizing your functional, then you have a metric that has some kind of things, and then it has a huge thing like this. So all the rest of the metric collapses, and then you see some bubbles that blow up. Or maybe a bubble that blows up is something like this. And here there is a conical point. So there are these two types of phenomena. Here is all the topology of the metric that is concentrated. So you see that in this case, the area is twice times 2 pi. There's 4 pi, the area of a round sphere. Here the area is 2 pi times 2 theta I, if this is xi. Because this is more or less the football at theta. So this condition, you remember that this weighted Euler characteristic is essentially the area of the surface. This is saying that the area of the surface is smaller than all the bubbles that can be created here. So basically,
as a result, no bubbles are created.
Yeah, there is not enough area to create bubbles. There is not enough area to have this type of degenerations. And this, well, in the mechanism of this direct approach or calculus of variations shows that you cannot have this type of degenerations. And then when you minimize the sequence, then you get really a true minimum, and then you get surjectivity, so the existence of the metric.
Your intention in constructing compactifications are to find the trace of the metric on the on the part where it vanishes, in fact.
Yeah. Yeah. So you want to somehow to blow up these regions. Yeah. So there are results of existence, so surjectivity also in the supercritical case, where these degenerations do occur. This is done in a different way by Bartolucci, De Marchis, Malchiodi. It requires some conditions. First, that you're not on those exceptional walls, but also that the angles are bigger than 2 pi, and the genus is at least 1 again. So you need some topology. So with Panov, we showed that this map, in fact, it can be non-surjective if some theta 1 is very small. If some theta is very small, so we're not in this situation, then there are conformal structures with no matrix. And another result that was proven by Luo Tian and then reproven later is that in genus 0, you can have all the angles smaller than 2 pi. In this case, the map is also injective. So in this case, there is a unique metric in each conformal class. So it's the only case in which there is this uniqueness statement, as far as we know, in this generality. And we are writing down a counterexample with Panov that in general, even in the subcritical case, but with some angle greater than 1, this map can be non-injective. So there might be, again, so you see that all these results seem to be quite tight. So as long as you weaken the hypothesis a little bit, then you get counterexamples. Okay, more topological properties. This map in general is proper, unless you are in these exceptional walls. But in general, this is proper. And I remind you that these are manifolds or orbifolds with the same dimension. So it's a proper map between manifolds with the same dimension. So in general, if we are not in these exceptions, the fiber is finite. And the degree of this fiber was computed. Very complicated paper I couldn't actually read completely by Chen and YCL.
That's what you mean by quantitative. Can be made quantitative.
No, this one quantitative is so the properness. What does proper mean? Proper means that if you are diverging here, then you are diverging in the target. So diverging here in the matrix can be measured by computing the distance, shortest distance between two conical points. I mean, this matrix crash only if two conical points crash. So here you have this distance which measures how far you are from degenerating. Here you have the shortest extremal length, which is extremal systole. So quantitative means that we could find an inequality between the length here, the shortest length, and the shortest extremal length here. That measures how proper it is.
And in the case of this paper,
Mm-hmm. This one?
This one.
Channeling, yeah.
The answer is understandable.
Yeah, it is understandable. It's complicated but understandable. They really write down a generating series. Yeah, yeah. They could pack the information into a generating series. Yeah.
And what kind of generating series they obtain?
It is a bit complicated. So they have a generating series with additively all these numbers, all these degrees, and this is equal to the product of other things that they put in. So it's the equality is written down this way. So there is.
It is explicit. Yeah?
It is explicit. Yeah, it's not a differential equation. It's really a sum equal to a product, and then you have to open up all the computations. Okay. So you see that here, in general, you have a finite. So there is a proper map within manifolds of the same dimension. You can compute the degree, but you are not sure. Here, the information of the degree tells us something about the generic fiber, but it doesn't tell us something about all the fibers. So in genus 0 with 4 conical points, none of which is integral, every fiber is finite.
Even in the case when all of them are rational.
Yes, yeah. But this is, he uses some tool about common zeros of two harmonic functions, real harmonic functions that is not available in higher dimensions. But the conjecture is that in general, all fibers are finite. So that in every conformal class there are finitely many metrics. But this is open now. Last thing, holomorphicity properties. So if we are in genus 0 with 3 conical points which are non-integral, exactly 3, all the others are integral, then you can put a complex structure on such space, and the map, the forgetful map, is holomorphic. So this was proven by Eremenko-Panov. If you have 2 conical points still in genus 0, you can factor the forgetful map, and this P is just an R bundle, so dimension 1, and this has a complex structure, and this is holomorphic. And if there are all are integral, then as we were saying, these are just maps to P1. So here you're factoring the automorphism of P1, so it's 3-dimensional, and this is holomorphic. So again, there is some holomorphicity property inside this forgetful map. But in general, there is no complex structure on such space that makes this map holomorphic in any meaningful sense. And the problem is really topological. So this map in the examples that we have really folds. So it's not possible to make it into a holomorphic thing. Okay, so let me say what we have in genus 1 with 1 conical point. So this is, as I said, one of the simplest cases. So the first result is that we describe the topology when theta is not odd. So this means that theta, so the angle must be at least 2 pi, but we are non-odd means that it's not 6 pi, it's not 10 pi, it's not 14 pi, and so on. So this space is an orbifold, orientable, connected, so dimension 2. And we can compute the genus. So M is just the real, the bottom part, the integral part of this theta plus 1 divided by 2. And one can compute the genus of such 2 manifold and the orbifold Euler characteristic. And the only, so all points are or have order, like in the modular space of tori, all points, all tori have this involution. So all points are orbifold of order 2, but there are some ones which have orders 4, the one which are coming from the square, and the hexagonal ones that have order 6. Here the same happens. So every point has order 2. Then sometimes there is a point of order 6. There can be at most 1, and this point exists if and only if you view theta as an element of the real line, the distance from the multiples of 6 is at least 1. This is just a compact way of phrasing the condition. And the same for orbifold points of order 4. There can be at most 1. We will see in the picture why. And there exists if and only if the distance is at least 1 from the multiples of 4. All other points have orbifold order 2. There is a special phenomenon when theta is even. Yeah. Okay.
Just one orbifold. We have just one puncture, yeah?
One puncture, yeah.
One puncture, yeah. Yeah, I see. And whether there is a natural complex structure on this MS11?
No, in general, no.
In general,
no. But in the case, in this special case, when theta is even, for example, angle 4 pi, or angle 8 pi. In this case, there is. And in fact, this moduli space with these special angles is really the quotient of the hyperbolic space by a discrete subgroup of SL2Z. So it has a kind of arithmetic meaning. And curiously, this subgroup has index m square, and it's not normal in general, except when m is equal to 1, which is the trivial case. So it's a strange kind of surface. Arithmetic, but non-normal. So the fact that it's non-normal, I am underlining this, it's important in some sense, because when it's normal, what you can think usually is that you have a homomorphism. How do you get a normal subgroup? You get it as a kernel of a homomorphism from SL to Z to some other group. And usually this homomorphism represents extra structure. So you think of a torus with some extra structure, then usually gives you normal subgroups. But in this case, the fact that it's non-normal shows that it's very difficult to view it as a torus with some extra structure in it. Okay, the other result deals with the remaining case, which is the case when it's odd. So angle 6 pi or angle 10 pi and so on. In this case, all the surfaces, all the tori are coaxial. So there's very exceptional case. And in fact, this orbifold now has a real dimension 3. So it is still an orbifold, but of dimension bigger than expected. And it is disconnected. Oriented but disconnected, and this is the number of connected components, and the connected components look like this. So it is this is the internal of a 2 simplex times r, but it is divided by plus or minus 1. So it's r mod. I'm describing the orbifold structure, so there is an action of plus or minus 1 on this r. And these are the components which have no extra orbifold point. This is the only component that can have these extra orbifold points. So this is a 2 simplex, but the internal part, but you mod by the cyclic group over the 3 that permutes the 3 coordinates. And then you multiply by r mod plus or minus 1. And so all the components are of the first type, and sometimes there is one of the second type. So there is one of the second type if m is congruent to 1 mod 3. Otherwise, they're all of the first type. So this is a brutally disconnected space.
In which case, infinite comparable to 1.
Yeah, because actually there is so there are many connected components, and these are somehow there is a bigger space on which Z mod 3 acts, and this Z mod 3 acts almost freely. But sometimes there is one triangle which is sent to itself. When there is this triangle sent to itself, we get this component. When there is no triangle fixed by Z mod 3, we get all components which are this type. Okay, about the forgetful map, this is not our results, but I will remind what is known. So in the regular case, so non-odd, this map, as I was saying, is proper, is finite by Eremenko, and Chen computed the degree of this map.
So the degree has been computed before. It has been proven that the map is finite.
Yeah, yeah. And well, finite. Sorry, because finite here means that every single fiber is finite. In their case, this is just a map between two manifolds of the same dimension, or a proper map between two manifolds of the same dimension, so the generic fiber has this cardinality. So here, in the even case, is still included in the former one, but this map is even holomorphic now. So all this holds, but now this is also a holomorphic finite map. This was already known, even though we showed it, reproved it. And in the exceptional case, the odd case, this is disconnected as we were seeing, and it's three-dimensional, so the fibers are these one-dimensional lines. And the more curious thing is that the image is not closed. So I'll show you now a picture of the image. in one example. So this is angle 6 pi. This is what you're seeing here. This is the modular surface. Here is the cusp of the modular surface. Here is the point of order 4. Here is the point of order 6. And this light thing is the image of the forgetful map in the case of angle 6 pi. So these conformal tori have a metric, a spherical metric with angle 6 pi. The darker ones do not. And there is this real analytic line in the middle that separates these two domains, which we called in honor link 1 lines because they studied it first. And in some cases we could write equations for these lines in terms of Weierstrass P functions. Okay. Yeah.
What is this separating point?
Which one? Here.
Yeah, here.
Well, it's not. Yeah, it's. This is okay. So this is a surface. So this segment is.
It's smooth, of course, but.
Yeah. This is a transverse intersection, right, between this curve that goes behind, right?
Yeah.
And this line. This segment is the tori that are spanned by 1 and tau of norm 1.
Yeah.
Yeah.
But this must be some point tau of norm 1.
Yeah.
Which point is it?
I don't know. And might be that Linger 1 we're studying it. So these ones, yeah, it should be something. Yeah, I don't know exactly geometrically which one it is. So I'm not sure that it's worth describing the construction. Maybe I will skip the construction in the flat case. I would go directly to the construction in the spherical case. Okay, let's go here. Yeah. Okay. I said to understand this moduli space, we reduce the study of spherical tori with one conical point to the study of spherical triangles. How we do that? So we pick a spherical torus like this. Now there is a conical point. The conical point is this black one. Here there is the conical point. And then we construct the Voronoi graph associated to this conical point. So we pick the distance from this conical point and we look at the critical locus of this distance. So the critical locus is this red one. So points on this red graph are points that have two ways of reaching x in the shortest time. You can go, if you pick a point, you can go this way or you can go backwards, I mean behind the torus and reach it from the other way. Points in the vertices, if the vertex is trivalent, have three ways. This way, that way, and this way below.
This is independent of the angle.
No, it does change with the angle. Yeah, it depends on the angle. So you pick a torus with its metric. You pick the metric. Attached to the spherical torus with its metric, you can attach this graph. And then you see that what happens if you cut along this red graph. You get a picture like this. The red ones are the red edges. Yeah, there is these A and B vertices which are repeated here. A,
so
B.
This graph and its combinatorics is invariant metric.
Well, generically, yes, but then if you start moving the metric, then at certain points there is gets 4-valent, like in the right case. Yeah. So and there are portions which are closer to the. You see here I colored in two ways. So if you take the transverse to each red edge, there is a blue edge, which I didn't draw here, which is basically take a point on the red edge, take two shortest way of going to x. So you take a point like P1, two shortest ways, there is this way and there is this other way. So together, if you take the geodesic, then they draw some kind of edge like this, and P2 draws something like this, and you have a third one. And this splits the torus into two regions. One which contains B, and one that contains A. The one that contains B is the lighter one. The one that contains A is the darker one. So
Once again, what's A and B?
A and B are the two vertices of the red graph.
Ah, okay.
Yeah.
For this particular value.
Yeah. These are
The angle.
yeah, an example. Yeah. And okay. So if you split this, and then you see that if you regroup the dark ones and the light ones, what you get two triangles. Now you should see. So one edge of the triangle is going from this x, P1, then you go on up to x. This is one edge. The other edge going this through P2, and the third edge goes through P2. Sorry, and the third edge goes through P3. So you have split the torus into two congruent triangles, spherical triangles. Here it's the limit case when the graph is 4-valent. You see, where the graph is 4-valent, you can add an extra edge in two ways, this way or taking the other diagonal. And in each way, you still decompose it into a union of two congruent triangles. But there are two different ways of doing it. It's not uniquely determined. Okay, so basically here we have described the moduli space reduces to study these triangles, and there are some identifications in this special case. So yeah, when the graph of this is the trefoil graph, then the decomposition in triangles is unique. When it's the figure 8 graph, then there are two possibilities depending on how we add the third edge. What happens here is that this...
Why do you use the term trefoil? I always thought it is a theta graph.
Is theta? Well, if you... Aren't there different... The theta graph, is it planar? Or depend?
Theta graph is just a graph.
Yeah, but these graphs have extra information of the cyclic order. These are like, yeah.
But why trefoil?
Wasn't this the trefoil? No?
Trefoil is just a knot. Trefoil knot, but I've never met.
Yeah, I don't know. This was, yeah. Okay, I cannot fully justify this name, but it's this graph, which is like the theta, but with the order which is different at one vertex at the other. Yeah. Yeah, in a different way. Yeah. So one important thing about this triangle is these two triangles that we get are what we call the balanced, meaning that their angles at the three vertices of the triangle satisfy the triangle inequality. And this one strictly. In this case, they are semi-balanced in the sense that they satisfy the triangle inequality, but one of the inequalities is an equality actually. Okay, so let me just go quickly. So how does one study the topology of this space? You have to study the topology of these balanced triangles, and because we reduce each torus basically to a balanced triangle, to a couple of balanced triangles glued. So if you're studying just triples, theta 1, theta 2, theta 3, with given area, so if you fix the theta of the torus, the area of the torus is fixed, so the area of such triangles is fixed. So once the area is fixed...
In general case, for general theta, how many triangles do you need to glue?
Two, always two. But then the area of the torus is given only by theta, by the angle, and so the area of these triangles is just half. So it's only determined by theta. So once you fix theta, so you fix the angle at the torus, at the conical point of the torus, the angle of such triangles is given. So the area of such triangles is the same as giving the sum of the three angles, theta 1, theta 2 of theta 3. So this simplex is the two simplex of triples, theta 1, theta 2, theta 3, whose sum is given 3.5 in this case. Now here we have seen that Gauss-Bonnet information is not enough in the case of triangles to say whether a triangle exists or not. So inside this, so this big black triangle is just Gauss-Bonnet information, and actually in the white region triangles do not exist. In the blue region triangles do exist. So these blue regions are triples of angles for which spherical triangles exist. These black dots, okay, this was the Eremenko's result that allowed us to draw this blue picture. These black dots correspond to the cases in which the triangles are not fully determined by the angles, but you can shift one vertex. In that case, if you are here, the space of triangles is one-dimensional. You can move that vertex. But here we are only looking at the triples of angles. So this we call it carpets. You see it as a union of such triangles and these black dots. And if you have a triangle, then you cannot touch its angle. It is bijective over the blue things, but as I said, over the black dots there is a segment coming from moving the point, one of the points.
So it is connected.
Yeah.
The moduli space is connected.
Okay, this moduli space of triangles, no, because you can see that this is not connected to this. You see that here is missing the black dot.
Ah,
Yeah.
Not at every vertex. Sometimes you have.
Sometimes, yeah, sometimes there is, sometimes there isn't.
So,
yeah.
so if there is a dot,
You are gluing these two triangles. Yeah, yeah,
a band.
yeah. But if you do not have the dot, then these are disconnected. So remind you what was the phenomenon. Over the dot, you have this segment given by moving this point A1. Yeah. And actually, in MT, instead of seeing this dot, you see exactly this. You see these two triangles, which have this kind of segment that is glued and gives you a smooth surface. So MT is a smooth surface. And when you map to the carpet, this black segment is collapsed to the dot. So the fact is that we were not interested.
So this picture on the previous slide, it's realistic. It's for this particular value, 3.5.
Yeah, yeah, it is realistic. Yeah. So in the fact is that, as I was saying, we are not when we cut the torus into triangles, we do not get just arbitrary triangles, but we get balanced triangles. So the angles of such triangles satisfy the triangle inequality. So inside this region, we cut in brown the balancing condition. The useful fact is that all vertices inside the balancing conditions are dotted, whereas sometimes there are undotted ones outside. So because these are all dotted, then we get something connected here. And inside, only inside we are sure that all the vertices are dotted. So from this picture, then it's just something elementary to compute the topological invariance, just to do some computations. So it's rather easy. You do all the computations and then you get. So why, just one thing, why do you get these orbifold points? Well, because when you get a triangle, here you see that to draw this picture, we basically chose which one is theta 1, theta 2, theta 3. But then these are just conventional. I mean, we can quotient by cyclic permutations. And if we act with Z mod 3 on this picture, well, sometimes in the center there is a fixed point, sometimes there isn't, depending on what the picture. In this case, there is a fixed point in the center. This one we get an orbifold order 6. Yeah. So you see here there is a fixed point. Here there is, here there is, here there isn't. Here there is again. Here there are these green points which are, so what is actually the true thing would be taking 2 copies of this, gluing and then acting with the S3 actually. When you act with S3 you can get this dot with pink point which is stabilized with stabilizer S3, or you can get this green dot which is fixed. This one is correspond to the point of order 4. I haven't spoken about this one, but so these are midpoints of the edges, basically. So one can draw all these pictures. So you can see that in this case, one can easily compute then all the invariants and whether these points do exist or not. Okay, so I think that maybe the time is almost over. So let me just, okay, this was the computation of the invariants. Let me just say one thing about the degenerate case, the odd case. Okay. So what happens with the odd case? Let me show you just an example. So let's do the example of angle 6 pi. So how do we get tori with angle 6 pi? We take a sphere, we cut along the sphere, we cut along a segment of length a plus b, and then we mark these some points. So the end points, this is x1 and this end point is x3. And then we put an x2 on this shore at distance a from x1. And then we put an x4 on the other shore at distance a from x3. Okay. So basically, if you want, we have three numbers, a, b, and c, whose sum is 2 pi, but we are cutting only along a plus b. And then we have four edges now, x1, x2 of length a, x2, x3 of length b, x3, x4 of length a, x4, x1 of length b. And we can identify a with a and b with b, as usual. This is a spherical quadrilateral, basically. It is a sphere, but the boundary has four edges. Identifying this in the usual way for tori, we get a spherical torus, and the angle picks a 2 pi here, a 2 pi here, a pi at x2, and a pi at x4. So it has angle 6 pi. So how many parameters are here? So there are two parameters, a and b, whose sum should be smaller than 2 pi. And this gives 2 dimensions. But then there is an extra parameter, which is a bit hidden. So you see that here the picture is a bit symmetric. So we cut along a portion of the equator. But actually, we can take the same picture and we can, as I was drawing the picture here, we can suck it a little bit along the North Pole. So we can take this flow that pushes everything toward the North Pole. And so this becomes a portion of the parallel, of a parallel here. And then we get another, the metric has changed. So there is an extra parameter, one parameter, that is telling us how much we are moving toward the North Pole or toward the South Pole.
Sorry, you make a cut not along a piece of great circle?
When you push, no. First, okay, the basic construction you cut along the equator.
Yeah.
Then all of this construction, you push it through this flow, but this flow sends the equator to a parallel, not to a geodesic. So it's same as cutting along a parallel, the moved construction. So there is a preferred one, kind of balanced one, that is invariant under the symmetry of the conformal symmetry of the torus. The other ones are not invariant. So here, this justifies why there are the three parameters. So the three parameters here appear, 2 because of a and b, and 1 because of these extra parameters. Why does one have many connected components? Because this is the basic construction. But then if you want something with bigger angles, you can cut along, say, x1, x2, and glue a half sphere along x1, x2, or you can glue 2 half spheres, and so on. And depending where you glue the sphere, you get different components. So the combinatorics enters because of the angle that increases. So let me show just the picture. So the picture is similar to that one. This is again the carpet. So now all the blue things have crashed into points, and so the domain has torn, and all of the ones that exist are just these points, and for every point we have a three-dimensional component. So this is the picture in the odd case. Okay, I think I've spoken already too much, so I think I'll stop it here.
Okay, let's thank Gabriele.
Thank you.
Very rich for the talk, which is very rich in material.
Could you open the slide, please, with this diagram for 3.8? 3.5
Yeah,
theta.
the one before.
Yeah.
Yeah. Okay, let's this one.
Yeah. So, for instance, do I understand correctly that in this case you have how many connected components do you have in this case?
For the moduli space, 1. It is connected.
But
The part inside the balanced.
the balance. But
Yeah, then there are some identifications in the boundary, but then
if it is not balanced, what's wrong?
well, it's not that something is wrong. So if you start with a non-balanced triangle, you can perform the construction and get a torus. The fact is that if you start with a torus and you take the Voronoi decomposition, then you get a balanced one.
Ah, okay.
So if you want sort of bijection, then you want only to consider the balanced ones.
Okay. So one and the same torus could be represented by different points, but only those which are balanced are unique.
Yeah, they can be represented by different points, but only one strictly balanced or 2 semi-balanced on the boundary.
Okay. Yeah, thank you.
Welcome.
More questions? Whether the knowledge of so what you were telling about is concerns only genus 0 and genus 1.
Yep.
Whether something can be constructed from the knowledge of this just by gluing surfaces of genus 0, for example. You can construct meteorized surfaces of arbitrary genus.
Yeah,
Do you expect, for instance, some new phenomena when you go to great, or just more complicated combinatorics? Some new phenomena?
well, for example, as I was saying, sometimes there is a different behavior, genus 0 and positive genus. For example, in the non-emptiness, we've seen that in genus 0 there are other constraints other than the Gauss-Bonnet, and this is depends on the fundamental group basically. So in genus 0, fundamental group is free, generated by the boundaries. In the other case, there are the commutators, and this gives some constraints in the monodromy that creates problems. And we don't know, for example, whether so in genus 0 we found a lot of connected components. Here too in genus 1, but if you see the connected components, there are many only in this kind of degenerate case, which is this coaxial of this method. But if you take away these degenerate cases, in the regular cases, the moduli space is connected in genus 1, always connected. We don't know whether it happens in higher genus 2. So we saw that in genus 0 it becomes disconnected, but it might be that even in genus twice or higher, in the regular case, it's always connected. This, for example, we don't know. And so we don't expect, I think that somehow the weirdest phenomena are probably in genus 0, I would expect. It's somehow the hardest case to be treated. I think that the mirrors, I don't know the paper well, but I think in the Gallo-Kapovic-Marden paper about monodromy representations of projective structures, I think that there they had also some problems in dealing with genus 0 surfaces with 4 boundary components. They said it was the hardest case to deal. So always the genus 0 when you're working with monodromy is always the hardest one, at least by experience. So I don't know exactly what phenomena to expect. Certainly the compactification problem is one of the most interesting, at least some meaningful compactification, something that can be useful, but seems complicated.
Is there any relationship between this picture and the cellular decomposition of the what was the name in the Conceived proof of Witten's theory? He used the cellular decomposition of the
same multiplication.
Sir, it was moduli space times
Yeah.
real octant.
Yeah, it is. This one is a little. It is similar. It is maybe a little bit more similar to Penner's version in the hyperbolic case, or Luo's with boundaries. So it is essentially the same. The only thing that changes is that in the negative curvature or zero curvature, for the existence of this decomposition in each cell, I mean, each cell was full in the sense that the only constraint that you had was something like Gauss-Bonnet. So every cell was contractible. Here it is not. So in every cell you see some kind of picture like this. So this is like what happens inside one of those cells. So that's why the situation here is more complicated. So they're not contractible inside. Yeah. So it promises one could, in principle, take Voronoi, like in general genus, and do. But then inside each cell, you will see some kind of a lot of holes like this, and so it's very difficult to control the topology. It seems at the moment difficult to control the topology.
Yeah, and representations of fundamental groups are a subject of cluster algebra study.
Yeah.
Do you expect any connection?
For instance, in M11 case, when you go through this boundary situation, you have just a flip. You have three triangles, but you do it in a different way. So observe flips, which
yeah,
often.
But yeah, I don't know if about cluster algebra. I'm not an expert. Do they coordinatize in the? I mean, the hyperbolic in Penner's case, right? They do occur. Yeah. So they are. So here is we're in the spherical. So maybe something must be slightly changed in the algebraic structure.
But since you get a symplectic structure, at least in some
Yeah.
situations,
Yeah, no, probably in that, I mean, one could write down the symplectic structure in those coordinates for sure. Yeah. It's the case, the SU2 case or SO3R case, yeah.
But that's the main and the starting, the basic case.
Yeah, the basic, yeah, the two basic SL2 and SU2. Right, yeah.
Okay, more questions? Yeah. Louder, Marina.
Like what kind of equations we need to solve to find the privileges under the Fourier map from MS to normal?
What equations we need to solve to detect what? The fiber?
The images, yes, the fiber.
Yeah, it is similar to the equation I wrote before. So before I wrote the real equation. Let me see if there was basically. Let's see if okay. Take a while. It was the Liouville equation in the case non-puncture case. Almost. It was almost, no, too much. Sorry. There was unpuncture case was still before, yeah. Yeah, that one. Okay, so in the so this is the equation for the if you have one metric, any background metric, and then you call K0 the curvature function of this metric, and then you want to get another metric which is conformal to the given one, the curvature K, then you have to solve this. Okay? Yeah. So, yeah.
So both k and k0 are not necessarily constants.
No, not necessarily constants. They're assigned functions. K0 is given by your choice, and this one is the one you want to get. So for example, if you have already, so if you want to look for curvature 1 matrix, then you get something like this. Now, if you have conical singularities, then this, instead of being just this one, there are some delta functions. So at point xi, there is a delta function of value. Now I have to understand, maybe 2 pi something like this. So you can okay, you can plug this and write it as in the distributional form, but here you have this delta. So what analysts do is that instead of this u, they consider another u tilde, and they sum a multiple, maybe 2 pi, of some green function at xi. So it's a primitive, basically, of the delta. So it has some logarithmic singularity, and when you take Laplacian of this function, you get delta. So you rewrite everything in terms of this u tilde, and then you get a differential equation with some poles with singularities. And that's what analysts do. So this is the analytic approach if you want to compute the fiber. Yeah, you don't want to. Yeah, so the problem is that with Panov, we didn't touch this aspect, because this is, yeah, it's very, very hard to, it can be useful to check what happens in a fixed conformal class, but it is very hard to move horizontally when you change conformal class, because you see all these equations are scalar equations, but once the conformal class is fixed. For example, even with this approach, which seems useful, analysts couldn't show that basically there are finitely many metrics, which would be the same as showing that you cannot deform this metric H. So if you have a spherical one, you cannot deform it to have a one parameter family of metrics. So they are isolated in the fiber. So they cannot do that. And so this approach at the moment has some limits. But there is no, geometrically, it's very difficult to detect what happens in a fiber. So for the moment, we do not have many tools.
Okay, if there are no more questions, then let's thank Gabriele.
Thank you. Thank you.